Okay, so let's backtrack for a minute. I just want you to have a chance to check your answers to example 4, B, and C, like I asked you to do before. I'm just going to leave them up for a minute. Even if you want a screenshot, if you're not sure, you can always, or pause the video right now and check if your answers are correct. So that is example 4, B, and C. I just use the conceptual method here because I feel like it's faster, but if you get the same answer some other way, more power to you. That's great. You can do it algebraically as well if you like. For part example 5, part C, I'm getting no solution. Isolating the absolute value first and getting no solution. And then for example 6, parts B and C, I solved them algebraically and then checked my solutions. And in part B, I produced an extraneous solution. And in part C, both of them worked. So it didn't have any extraneous solutions. But you have to check, especially when there's a variable on the inside and when there's one on the outside, is really a good clue that you should be checking. Technically, you should always be checking your solutions back into the original equation and see if they work. So now the question is, why is this happening? So that's like the most interesting question. Out of all of these, like we can do all the mechanics, but why do we sometimes get extraneous solutions when solving absolute value equations? And what happens geometrically? Well, first off, when we solve algebraically, oh, now I can't find my pen. Here we go. When we solve algebraically, what we do is we make some assumptions for ease of use, essentially. So if I looked at, I can just go back and grab the first problem here. Let's see, it said the absolute value of 3x plus 1 is equal to 4x minus 5. So when I look at that, I'm going to do the positive and the negative version. But as soon as I rewrite them as positive and negatives, right, I am rewriting it, how it behaves. So then all of a sudden, the absolute value is gone. So I'm treating the positive version as just something without absolute value and the negative version as something without absolute value. So I had 3x plus 1 is equal to 4x minus 5. So for algebraic convenience, I'm actually changing how the equation is behaving. But it's just so we can mechanically find the pieces. So, and the same for the negative version, negative 3x minus 1. I'm just distributing the negative right away. 4x minus 5. So I am changing how the equation is behaving. For algebraic convenience. Oh, I forgot an A here. Algebraic convenience. So that means we're just doing it, changing it slightly so that I can get something algebraically. But what happens is when we change how something behaves, we can then end up producing extraneous solutions. So by changing the behavior of the equation or of part of the equation, we now can potentially produce extraneous solutions. So we might produce stuff that aren't necessarily true, but look, it's working. It's making it work. At least we narrow it down. It's not that before I started, I had no idea what x could B, but now I've narrowed it down that X could potentially be these two things. It might just be one of those things, or nothing might work, but it narrows the field down to a lot less than having to consider and substitute in every X in the world and see what works. That would take forever. That's called the numeric approach, by the way. The other way we could think of it, just to explain it a little bit better, and if you're much like me, I think more in pictures than I do in algebraically, believe it or not. So if I looked at that, the geometrically, what's going on? Well, I have this, I'm going to use the same example temporarily here. I'm still going to use this one. Right now, we have one variable only, okay? When we're solving in one variable, we are on the number line. So what I'm going to do is I'm going to temporarily introduce another variable to help me explain this. So let y sub 1 equal the absolute value of 3x plus 1, and y sub 2, so that there's two different y's. Well, we're looking for, it's going to be 4x minus 5. So we're looking for where y1 is equal to y2, essentially, because that's here. This is y1 and this is y2, the two sides of the equation. That, what it does is now I'm going to put it on the coordinate plane, which sometimes makes it a little bit easier to see and understand what's going on with the two, but it's only a temporary measure because technically it's only in one variable. So I'm just doing it to help me understand what's going on with the values. And the way that absolute value works, okay, if you have absolute value on one side, you're actually going to get something that is V-shaped like this. So on the left-hand side, I'm going to get something that looks like y1, like this. And on the right-hand, so here is my y1. I'm going to underline that. And on the right-hand side, I'm getting what we know from Algebra 1 is a line. So if I'm getting a line here, there's lots of different ways. If you think of a V shape, you end up with the V shape here, and then the line could intersect like this in two places. Or I could have the V shape, the absolute value, and the line could be steeper than the two sides of, and it could intersect like that. That means it only has one intersection. Or it could potentially look like this, and then the line is down here, and it doesn't intersect the absolute value at all. That would be no solution. For the first one here that I'm highlighting on right now, produces two solutions. This one, where the line is steep, as steep or steeper than the branches of the absolute value, it's only going to produce one solution, and the last one down here on the bottom will produce no solution. So we have lots of options here, and what happens is when we do this algebraically, the one we did, the first one, it happens to look like this. It's a steep one. Oh, I'm not a very good picture. Maybe I'll fix this one. Y1 is actually, it'll do this. Oops, like that. And then they intersect only in one place over here. But then why do we get this extraneous solution? Well, before, when I was talking about the algebraic assumptions we were making, it makes the assumption, if you look at it, instead, when we do the positive and the negative side of it, if you look at the side where the absolute value used to be, I'm not now making the assumption, oh, that's a line. So what it does is it takes this V shape and extends, instead of making it a V, it extends it out. And the same on the other side here, this one here, it now extends this side out here. And the extraneous solution ends up happening on that extension down here. So when we make that algebraic assumption, it's the one that produces the extraneous solution is the one that hits down there. So for example, if I had something that ended up having none of the solutions working, so we would get two extraneous solutions, what we were doing algebraically is making an assumption that there are two intersecting lines, and we end up with two intersections on those extensions that are actually not intersecting the absolute value, because that's what we want. We want to figure out where the line is intersecting the absolute value, and it's not. But when we make those algebraic assumptions, we are creating two intersecting lines rather than the V shape. So essentially, we're changing the behavior of the absolute value.